Your phone is roaming in another country. A video call still works. Behind that simple moment, control messages have to cross from one mobile network to another through a third party interconnection fabric called an IPX. Here's the puzzle that matters. Those two networks, called PLMNs, public land mobile networks, do not fully control the middle. So, how can they exchange the messages roaming needs without simply trusting every intermediary on the path? Think of a border crossing between two countries. People and goods must move, but you would never leave the gate unguarded. In 5G, the same tension appears at interconnection. Operators need connectivity for roaming. They also need assurance that signaling is authentic, confidential where required, and not silently rewritten in transit. This lecture follows that border crossing idea from first principles. We will watch how 3GPP Release 15 places a security guard on the control lane, how two guards negotiate the rules before traffic flows, and why the user data lane stayed thinner until Release 16 added its own checkpoint. Hold one question in mind the whole way: which traffic is being protected, by whom, and under what negotiated rules? The first answer in Release 15 is a new boundary entity, the SEPP, Secure Edge Protection Proxy. Picture PLMN-A on the left and PLMN-B on the right, with the IPX sitting between them. Inside each PLMN, live network functions, the NFs that handle registration, session setup, and policy. At the edge of each PLMN stands a SEPP. It is not a random middle box. It is the deliberate security perimeter for roaming control traffic. Here is the rule the standard locks in. All roaming control traffic is routed through the SEPP and across the N32 interface to the other PLMN's SEPP. A control message does not wander out of PLMN-A and hope for the best. It goes to SEPP-A, then over N32 through the interconnection path, then into SEPP-B, and only then toward the peer network functions in PLMN-B. TLS protects the hop between SEPPs and also the hop between a SEPP and the next hop intermediary in the IPX when that topology is used. Pair by pair, SEPPs negotiate which security capabilities they will actually use. That negotiation matters because not every interconnection looks the same. Some paths are more direct, some pass through IPX entities that may need to see or transform selected fields. Pause on the plain language takeaway. Control traffic does not cross the interconnection unguarded. It is forced through paired boundary proxies that speak a defined interface, N32. One misconception to kill early. The SEPP story in Release 15 is about control and service-based signaling between PLMNs. It is not automatically a full story for user plane packets. We will return to that second lane later. For now, the control lane finally has a named guard. A single encrypted pipe sounds enough, until you notice what the interconnection actually needs. Two SEPPs must first agree how the real signaling will be protected. That agreement has its own channel. On the diagram, look at N32C. N32C is a mutually authenticated TLS connection used to negotiate security for N32F. Say that slowly, because the split is the whole design. First, the two SEPPs authenticate each other with TLS. Mutual authentication means each side proves identity to the other. Second, that authenticated channel is labeled N32C, the control conversation about security. Third, the outcome of that conversation decides how N32F will be secured. N32F is the path that will carry the actual NF-related signaling between the networks. Visually, derive the relationship in 3 beats. Establish mutual TLS between the SEPPs. Name that channel N32C. Let N32C set the protection mode for N32F. Why not fold everything into one anonymous TLS tunnel? Because the path may not be a clean SEPP to SEPP hop. When traffic goes through IPX intermediaries, the protection model has to account for what those intermediaries are allowed to do. Negotiation on N32C is how the endpoints decide the rules before the busy signaling path opens. Plain restatement: N32C is the conversation about security. N32F is the signaling path whose protection is being decided. If you mix those two labels, the architecture collapses into a vague, just use TLS, and you lose the negotiation step that Release 15 actually standardized. Now open N32F. This is where NF-related signaling rides after the rules are set. N32F is not one fixed mechanism. The source shows two legitimate branches, chosen according to topology. Branch 1, a direct connection between SEPPs. In that case, TLS can protect N32F end-to-end between the proxies. The path is clean, the protection model is familiar TLS confidentiality and integrity for the hop. Branch 2, a connection that passes through entities in the IPX. Here the standard points to PRINS, Protocol N32 Interconnect Security. PRINS exists because intermediaries may need controlled visibility or controlled modification of selected JSON information elements. A blunt end-to-end TLS tunnel that no intermediate can touch would block legitimate interconnection functions. PRINS is the answer tailored to that reality. Watch the misconception form, then cut it. People hear TLS on N32 and assume every N32F path is identical. It is not. Direct paths can lean on TLS. Paths via IPX entities lean on PRINI after N32C has negotiated the terms. So the architecture is topology aware. The same interface name, N32F, carries signaling in both cases. But the protection technology follows the path. That is why negotiation came first. You cannot pick the right branch until both SEPPs know what the interconnection looks like and what each side can support. Zoom into PRINS. Do not treat it as a magic label. Build the agreement the way the SEPPs do, piece by piece. Before NF-related signaling travels on an IPX-mediated N32 TASH path, the endpoints must agree on cryptographic tools and on policies for information elements. First, keys. Both sides need shared keying material, so protection is not theater. Without agreed keys, encryption and integrity checks cannot mean the same thing at both edges. Second, cipher suites. Keys alone are not enough. The algorithms, how you encrypt, how you authenticate, must match. Cipher suite agreement is the concrete choice of those algorithms. Third, IE protection policies. IE means information element, fields inside the JSON signaling. Not every field is equal. Some may be encrypted so intermediaries cannot read them. Some may carry modification protection so a change is detectable. The policy says which protections apply to which elements. Fourth, the two protection intents the source's name explicitly: encryption and modification protection. Encryption hides content. Modification protection detects tampering. Together they answer the border-crossing fear. Can someone in the middle silently rewrite a critical field? Imagine a rule sheet filling in as N32C completes. Keys? Agreed. Cipher suites? Agreed. IE policies? Agreed. Encryption and modification rules? Agreed. Only then does the PRINS protected signaling path open. Plain restatement. Before the message travels, the endpoints agree on what protection means and which cryptographic tools they will use. PRINS is not security somewhere in the middle. It is negotiated, element-aware protection for interconnection through IPX entities. Return to the border. Until now, we have been staring at the control lane. SEPP, N32, TLS, capability negotiation, PRINS. Split the crossing into two lanes. Lane 1 is control and service-based signaling. Release 15 gives it a detailed story. Route everything through SEPPs, protect with TLS toward peers and next hops, negotiate capabilities, and use PRINS when IPX entities sit on N32F. Lane 2 is the user plane, the actual user data packets that carry the video call, the download, the bytes the subscriber notices. Here, Release 15 is deliberately thinner. The sources state it plainly. No specific protection mechanisms are standardized for the user plane between PLMNs in Rel 15. VPN techniques may be used. That sentence is easy to underread. It does not say user data is free for all. It says the 3GPP REL 15 Interconnection Security Enhancement Package did not standardize a dedicated SEPP like mechanism for Inter-PLMN user plane the way it did for control. Operators may still apply VPNs or other transport protections, but those are options, not a new named 3GPP interconnection procedure on the same footing as N32 and PRINS. Why does the gap matter? Because a student who only learns 5G interconnection is secured by SEPP will overclaim. SEPP secures the control interconnection story. The user plane panel in REL 15 is a separate, less specific panel on purpose. Plain restatement. REL 15 gives a defined interconnection security story for control traffic, while the user plane panel remains intentionally less prescribed. Release 16 answers the missing lane with a named checkpoint. IPUPS, Inter-PLMN User Plane Security. IPUPS is not another SEPP. It is new functionality in the UPF, the user plane function. Roaming user plane messages are routed via IPUPS. The enforcement point the sources highlight is GTPU security on the N9 interface between the visited PLMN UPF and the home PLMN UPF. Watch the path assemble. In a visited network, user packets enter the visited UPF. For inter-PLMN roaming user plane, traffic is steered so IPUPS participates. Across N9 toward the home PLMN UPF, IPUPS enforces GTPU security. The home side symmetrically sits behind its own user plane edge. Compare the two releases side by side. REL 15, Rich Control Plane Interconnection Security via SEPP and N32. User plane left to non-specific or VPN-style options. REL 16, still keep the SEPP control story, and add IPUPS so the user plane lane has an explicit function and an explicit interface, N9, where security is enforced. A useful analogy. REL 15 built a proper passport control booth for official documents, the signaling. REL 16 adds a cargo inspection lane for the goods themselves, the user packets, with inspectors stationed at the UPF border on N9. Plane restatement. The later release adds a named user plane function and a stated security enforcement point. Control and user plane now both have first-class interconnection security concepts, enforced at different places by different entities. Zoom out and hold the whole argument in a few clear lines. First, SEPPs place security boundaries at the edges of interconnected PLMNs. Roaming control traffic is forced through those proxies over N32 instead of crossing the IPX unguarded. Second, N32C lets SEPPs mutually authenticate over TLS and negotiate how N32F will be protected. The negotiation channel is not the same thing as the signaling channel. Third, N32F carries NF-related signaling. A direct path can use TLS. A path through IPX entities can use PRINS, after agreement on keys, cipher suites, and IE protection policies, including encryption and modification protection. Fourth, Release 15 left Inter-PLMN user plane without a specific standardized mechanism, though VPNs may be used. Release 16 adds IPUPS in the UPF and enforces GTPU security on N9 between visited and home user plane functions. The broader idea is layered security. Different traffic classes get different mechanisms and different enforcement points. Control signaling needs identity, capability negotiation, and element-aware protection when intermediaries are present. User data needs its own path controls at the UPF boundary. One slogan never covers both lanes. Here is the open question. The same style of reasoning can attack next. If control plane and user plane traffic need different protections, what other paths in a roaming architecture, charging interfaces, lawful interception touchpoints, or management planes, might require their own boundary and their own negotiation rules? Keep the border metaphor. Ask, for every new interface you meet, who stands at the gate, what is being negotiated, and which lane is actually moving.